I'd like to introduce a new method that was added last year to VBox Wrapper in version 26.206, and this new modification adds or enables the VBox Wrapper to deal with multi-attach mode and differencing images within VirtualBox. So my name is Stefan, but you may know my other name from my nickname from different BOINC forums, especially from the LHC at Home forum. I'm from Germany, better from Upper Franconia, which is part of Bavaria. I'm a BOINC volunteer since mid-2008, running different projects. At the beginning, smaller projects, since my internet bandwidth was very low. But I prefer to run LHC at Home today. Maybe since 2012, 2013, since I have enough internet bandwidth to run those projects. So first thing regarding that change is to recall some basics about the BOINC project setup, because they will get important for the implementation. First, let's look at the classical application setup, like TN-Grid uses it, or we've heard about Sixtrick in an earlier presentation. Sixtrick uses also this project setup, which is the BOINC client is responsible for transferring data between the server side and the client side, and puts data and files that are required for the tasks in a projects directory. And when the BOINC client schedules a task to run, then it transfers a couple of files from the projects directory to a slots directory, an indexed slot directory. So slot 0 or slot 1 you can see here. And this example is as saved from the TN-Grid. We have a single executable file. You can see it here. Well, it's not exactly the file. In that case, it's a soft link, but from the perspective of the task, it's inside the slots directory and refers to the executable file here. So this is a very simple setup of a project task. If things are getting more complex, we need a bit of more complex setup, but the principle from the BOINC client is nearly the same. We have also a projects directory where the files are stored after transfer from the server and to the client. And then in this case, it's an example from LHC at Home. It's a theory native task. And you can see in the project directory, we have a wrapper that is used as an executable file. And this wrapper is able to make a much more complex setup in the slots directory, while from the BOINC client's perspective, it remains a single application. So those kind of setups are used in this example for theory native, where some kind of a container app is used, run by runc at the end. And it is also used in case we have GPU apps, because the BOINC client itself is not able to control all the various signals from GPU apps or feed all kind of GPUs, sorry. And we also have those kind of setup if we use virtual machine apps. And on the next slide, I'd like to encourage you to forget for a very short moment all about BOINC, but let's talk about what is a virtual machine. A virtual machine is a high-level definition or term to abstract and explain complex computer architectures with words that users and volunteers and computer users usually are familiar with. This is, for example, a computer is made of a CPU, is made of RAM, is made of a storage like a hard disk or SSD or something like that, or a device. And if we talk about a virtual computer, this can be seen as a device or a machine that is defined in the same way than a real physical computer, but it's located inside a real physical computer. And so that way you can have multiple virtual computers inside a real hardware. So what you need to control this is typically called a hypervisor, and there are several hypervisors in the market. For example, VirtualBox. We have Hyper-V that today most people know from Microsoft Windows. We heard about QEMU in the presentation before, and there are a couple of other emulators or hypervisors around. So on the next slide, we see a typical screenshot from the VirtualBox graphical user interface from the VirtualBox manager, and you see all of that what people expect to be part of a real physical computer. Here in the manager of the VirtualBox, you see you have a computer, in this case a virtual computer that has an operating system. We have a base memory, we have a display on that computer, we have a storage device, and what is not on the screen, we of course have a network device that can be attached to a network. But this is all of that is virtualized. So the VirtualBox software suite is responsible to map these terms to the real hardware. And in that case, we have, for the virtual machine, we have predetermined hardware. This is given by the real physical hardware we are running that on. For example, if we run a computer, a physical computer having an Intel CPU, the virtual machines on this physical computer will also have an Intel CPU. The same happens for AMD also. So okay, what I missed is that this wrapper that we now have as a part of the BOINC software suite controls the setup and the setup and the control from the virtual machines on this physical computer by a command line interface also included in VirtualBox. So we have we have this chain, we have the BOINC client on one side and we have the virtual machine on the other side. And in the middle of that all, we have the VBox wrapper that uses use this VirtualBox command line interface to set up a virtual machine with distinct specs. Some of them are hardwired, like net networking, and others are configurable to meet project needs like RAM size, disk size, or that is missing here, in some cases, number of CPUs for that virtual machine. Okay, let's have a more closer look to the storage device, because that's the change that was made last year to the VBox wrapper. So how is a virtual disk defined and attached to one of those virtual machines? So what you'll see here is in the projects directory, we typically have a VDI file. That's a file format that is specific to VirtualBox. And this VDI file represents the physical disk that we would normally have on a physical computer, but in this case, it's a file that includes all things that we normally would have on a physical disk. This physical disk, this VDI file, is then transferred to the slots directory, and BOINC defines how to do this in the traditional way. That means the traditional way was to rename this VDI file to VM_image. This is hardwired in the older VirtualBox VBox wrappers, and this file is copied, as I said, to the slots directory. Then, as a requirement from VirtualBox, this file is given a new UUID. This is for administrative reasons inside VirtualBox. And then the new image is opened in read-write mode to make it possible to store results on that file, especially from the perspective of the virtual machine, to store results and logs and everything on the virtual disk. So in the old method, it was hardwired that each task gets a full copy of the original VDI file. So as you can see here, we have one example from theory, from a theory application from LHC at home, where the original VDI file has roughly 780 megabytes. And when this is transferred and after a while some additional data is stored to that disk, it slowly grows. But the important thing is that at the beginning of the task, when the task is started and starts to run, then we have a peak disk usage, a peak I/O usage of 780 megabytes that have to be transferred to the slots directory. In this case, the 780 is relatively small. And if we look at other projects or even sub-projects from LHC at home, we have sometimes much larger files. For example, this is the theory file we see here, 780 megabyte. It's less than 1 gigabyte. Atlas, another sub-project, that also runs VirtualBox machines, has 2.5 gigabyte. CMS at the moment, so about 3 gigabytes per VDI. And if you look at Rosetta, they ran VDI files that had an initial size of roughly 7 gigabytes, which puts a high load on the I/O system at the beginning of each task. So if we make a closer look to the VDI files, what is the contents of those files? I have an example. This is from CMS, from LHC at home. The blue field is roughly the OS, operating system. In this case, it's a Linux operating system that has 650 to 700 megabytes. And the red portion of this VDI file is CVMFS cache. CVMFS is a network file system that is preloaded on this VDI files and is a snippet of a huge repository, a huge internet repository that is required to run those tasks inside the virtual machine. And then we have a yellow portion. The yellow portion is the files that are created and stored on that virtual disk during the runtime of a task, which can be several hours. In this case of CMS, it's roughly 12 hours. So we see we have a large high load on at the beginning of the task because the 3 gigabytes have to be transferred to the slots directory, and then over a period of roughly 12 hours we have an additional load of much less than this 3 gigabytes. And that's the issue. And the idea that came up last year was to solve this issue with this high load. And since most of the tasks, especially the CMS tasks, access this CVMFS cache, how can we manage this to make this cache that is already in the basic VDI file, how can we make them available to all tasks that are running concurrently, because this data doesn't change. So the solution is given by VirtualBox itself, because VirtualBox, since version 4.0, is able to attach a VDI file in a special mode, not in normal mode, but in a special mode called multi-attach mode. And this multi-attach mode multi-attach mode allows us to use the VDI file in the projects directory in read-only mode, and opens it in read-only mode for all for all virtual machines that are attached to that VDI file. And inside the slots directory, we now have in the snapshots directory a different image file, a different VDI file that is automatically created in read-write mode by VirtualBox. And this is given an individual UUID and a reference by that UUID. And this is done for every task for every VM we run concurrently, and handled, as I said, by VirtualBox itself. Oh, so I'm missing some slides. I'm not sure how where they are gone. Okay. Yeah, I'm sorry. I'm missing some slides with some explanation. Yeah. Okay, but those slides were yeah. Well, that was a bit incomplete. I'm a bit confused now because I prepared some additional things, and they are missing now. I'm not sure where they are gone. But I think you understood the principle, and what is the benefit now? We have much less peak load at the beginning of the task, and we have much less data transfer at the beginning of the task, and that allows at the end a user to run more tasks concurrently. So well, thanks for listening so far, and I think there are some questions now. Feel free to ask questions.